Hello, everyone. It's a pleasure for me to talk about the Marc 2015 release. And we'll start off first in saying that this is really the third release of calendar year 2015. And we plan on releasing it literally in the next few days to 1 week. So let me give you first a brief overview of what's in Marc 2015. We always try to talk about certain themes of the release, and the release themes include material behavior, always particularly this release on rubber or rubber-like materials, but also some metal plasticity as well, contact advancements, ease of use advancements, and some advancements in the area of durability, which really involves basically fracture mechanics and adaptive meshing type technology. So all these things on the right, I hope to briefly go through here today with you. I'm really going to start with ease of use, and the first thing that I want to talk about is some of the enhancements that have gone on in the area of application of boundary conditions on solids. Many of you might remember that a few years ago, the Mentat product used ACES as its solid modeler, and we were able to put boundary conditions on what it produced, which was NURB geometry. And then we've been moving to using parasolid geometry, which gives us better synergy with most of the CAD environment and the other MSE products. But we weren't able to apply boundary conditions directly on the geometry. Now, in fact, we can. And what we could do is we can apply boundary conditions on either vertices, edges, faces, or solids. And then, of course, when we generate the finite element model, effectively those boundary conditions in this particular case of applied displacements get immediately transformed to the finite element mesh. But I also want to highlight that one other thing that was done in the 2015 release was also we had introduced a concept called model sections. That was a powerful technique to basically do process simulation, where you would first generate one simulation and then at some subsequent time take the results of that simulation and move it to something else, transfer the data through model sections. In the past, it was difficult to apply boundary conditions to these model sections. So with the 2015 release, you'll also see that we can apply boundary conditions to these model sections. That's both in this case of a fixed displacement menu or in the case of distributed loads or other things as well. So the menu that you're normally familiar with in terms of applying boundary conditions is much more sophisticated than it was before, but it's very, very powerful. And to really talk about that power, I want to talk about really what we can now do with associativity and generative nature of the product. If we would have had this particular CAD model and we applied this distributed load to this particular face, and then if we had generated a finite element mesh, as I mentioned, those pressures would have been immediately transferred to the face. But now if I said, let me remove the holes on this particular solid body, so I go into defeature and I identify all the holes, and they show up in this lighter shade of blue, and then let's say I remove that group of holes, then effectively what happens is the holes would have been removed. It would have automatically generated a new finite element model for you, and it would have applied the boundary conditions onto that new finite element model. So this is a great productivity tool when you're doing small design changes or if you want to suppress these features, because clearly by suppressing these features, we got a coarser mesh and lower computational expenses. Other things that we did in terms of ease of use is we added a drop and drag feature through the model browser. And I think every release of the model browser is getting more and more powerful. And I think there's a group of folks who really aren't using that top bar anymore, but do everything through the model browser. But in this particular case, we would have had a set of boundary conditions. They could be of different types. We could have selected the particular boundary conditions and directly moved them into this load case. And then if one would have opened up the load case, you would have seen that those that we had selected were now in that load case and were now being activated. And there are a lot of things that we can do that way, whether or not it's the boundary conditions I mentioned previously, or whether or not it's contact table into load case or job, or adding a mesh adaptivity in load cases as well. Another really powerful capability is clipping planes. And there used to be a capability in Mentat, but it really didn't generate very nice plots, and it wasn't particularly fast. And so we have a new capability that can be used in both pre-processing and post-processing, where one can generate a particular plane. It's easy to do, easy to select what the normal is, where the location is, and you can then move the plane through the body to really see the incremental behavior associated with it. So we can see into the body, and we're going to see a few examples of that as well. But of course, it works in pre-processing as well. This was about a 1 million element engine block, and we could have created a plane and said clip all the elements above the plane and get the bottom of the block, or we could have said clip everything below the plane and get the top, or of course we could do it at any arbitrary angle. And there are really very interesting things you can do with this. And this is a case of, we've been talking lately about a lot of fracture mechanics. This was basically looking at a crack propagation and then effectively dividing the body. So it's very difficult normally to see inside a 3D structure, but here we could see the crack propagating through. Another nice feature of this is we can take a look at a structure like this, and we can isolate critical regions. So this was a rubber bushing. It's a standard example, but in the post-processing mode, you'll see this thing called model clipping and settings. And what one can do is take a look at the model, look at the strain energy, and say, I want to focus on those elements where the strain energy was greater than 0.4. And it will give you a subset of the model, of the mesh, where the strain energy satisfies that particular constraint and removes all the rest of the elements. And then what you can do beyond that is you can say, okay, now that I have that set of elements, why don't I take a look at what the von Mises stresses are? So we're seeing one quantity, the von Mises stresses, on those elements that have the region of the highest strain energy. So it's a very powerful procedure. We can also scale the displacements so that normally we always talked about you took the deformation and the deformation was uniformly scaled. Now it can be non-uniformly scaled. Again, a crack propagation is a nice example. Normally this distance is very thin, but we said scale things in the third direction, and so it will show really a magnified deformation based upon that particular scaling. Of course, it's important that you're not confused. So now when we do that, we basically put down what was the scale factor that was being used in the simulation or in the display of the simulation. There's some other nice enhancements associated with Mentat. One of them has to do with keyboard shortcuts. Sometimes our menus are a little bit too deep, but you can basically use one of our pre-programmed ones, or you can program things yourself. My favorite one is the distance command. So I can just say Control-D, and it moves directly to distance and asks me for my different points. Another one has to do with the file browser. We have a new procedure. People were confused a little bit about where they were. So the file set directory does one thing, and then you can basically always say, where am I, and go to my current directory to locate particular files. That's very useful. Sometimes we want to look in one directory, but let's say we want our graphic files to go into some other directory. And finally, on Mentat, there's a new user's guide. It's new and improved. It's based upon HTML. And we have a procedure now that we can really guarantee you that the figures that you're going to see in the user guide are going to be exactly the same as when the product runs. And for those people who are learning the product, every one of these user guides at the end has a button that says Run Analysis. And you click that button, and that particular example problem will run. So it's a great training tool for your colleagues who are just beginning to use the Marc and the Mentat product. Okay, let's talk about nonlinear analysis. And the first material model I want to talk about is what's known as the Payne effect for modeling effectively the viscoelastic behavior of rubber and elastomers, where we have not only a frequency-dependent damping, but we also have a damping that's dependent upon the amplitude of the excitation. So many rubber materials show this particular behavior, and we recently, modernized the capability for frequency-dependent elastomer behavior, but now we have this other capability as well. So you can think about this as effectively the storage modulus and loss modulus of the material being a function of both frequency and the amplitude. So what this really does is it makes that harmonic simulation really a nonlinear harmonic simulation. So we basically apply some preload, we apply a excitation onto that preload. We basically take a look at the amplitude of the results, and then we use that amplitude of the results to tune the damping and run this again. So we're running really an iterative loop within the harmonic excitation. And it's an important phenomena in the sense that there are many materials that if we excluded the Payne effect, what would happen would be the critical frequency would always remain the same. And if we would have doubled the excitation or tripled the excitation, the resultant value would be linearly dependent upon the excitation. But when we include the Payne effect, what really happens is two things. One is based upon the amplitude of the excitation. There's a shift in the critical frequency, but in addition to that, the response is not linearly proportional. And in the Marc product, what we've done is we've introduced a large number of variations of models that one can do, and they have different levels of sophistication. Let's start with the top one, which is the most sophisticated way of doing this. But there are others as well. This one is quite popular in the automotive industry because it only relies on 8 parameters. And the one that's perhaps the nicest one for you to enter is really based upon a table, where we only need to enter our storage and loss modulus as a function of the amplitude and the frequency and perhaps the table. So one of the things that's going on, of course, is we've been introducing more and more sophisticated models, and we are working to enhance the material characterization, or you could say the material parameter values, and that will come out in a subsequent release. So, of course, everything that we can do introduced on the side of Marc 2015 is available for the GUI as well. So we can basically add this type of behavior to all the traditional rubber-type materials. Here it was basically an Ogden material, and one could basically say that we wanted to include the Payne effect. When we do that, that's only in the frequency domain. That's not in the time domain. And then effectively what was chosen here was the Viscoelastic model. There's a nice feature in defining load cases. So this, of course, is a harmonic load case. And, of course, we set, the frequency range that we want to do the analysis. But we can give this harmonic load factor. And what that basically says is, how much should we scale the load? So in that previous example, I scaled the load 1, 2, 3, and then we could do something similar so you don't have to apply the boundary conditions. Similar, there's some new postcodes available for interpreting the results. So this was a particular example. It was a little bushing model, and again, you see that effectively that there's this frequency shift and a nonlinear behavior. The next material model I really want to talk about is a nonlinear elasticity with permanent set. And this is also for carbon-filled rubber materials. This is something we go into the laboratory, and we basically see a behavior where we have nonlinear elasticity. We don't really follow back the same range. And what happens is the more strain we apply, we end up having this so-called permanent set. So this model, which we call the parallel rheological framework, has a contribution that's nonlinear elastic, viscoelastic, and we use the word plasticity, even though it's not really like metal plasticity, and damage as well. And it's called a parallel network because it really is looking at all these different terms in kind of a generalized Maxwell concept where we have a purely elastic behavior, then we have effectively some viscoelastic elements, and then these permanent set elements as well in the model. And again, for any types of material model, this is kind of whenever you look into Mentat and you basically say, I want to define a material, and even if it would be an isotropic material, under the material selection, you're going to see something that says single network or multi-network. And if you're not using this model, you're always going to be a single network. But when you want this model, you would basically identify the multi-network, and it would ask you, what do you want for your material, for your viscoelastic behavior, and what type of materials models do you want to use to represent the permanent set or the so-called plasticity behavior. So this is the first example. This is basically a model which was elastic and basically viscoelastic. And we really could have done something very similar to this using, let's say, the Bergstrom-Boyce type of model, but here it was done with this type of behavior. And if you can think about this, here was the CO, and here we loaded a little bit more, and this is a standard example problem in volume E. We closed the model. We basically got our contact status using double-sided contact. We basically opened the door. We left it here in some sort of viscoelastic nature. This is done very quickly, and then we basically let it go for a long time, and it relaxed to this state. And in the case where we had plasticity or permanent set, we closed it as well, really the same contact status. It opened up. We removed the door. There was a certain element that with a long period of time would effectively relax to this particular state, but there's still permanent set in the particular model. And what we can do on these types of problems is we can effectively capture what are the residual strains, just as if we're doing a plasticity model as well. And what one observes, if you would look at different points here, is that point that's really undergoing the largest amount of strain. So we have our nonlinear behavior. We have some unloading, including that's also a nonlinear behavior. Then effectively what happens is we have a certain amount of viscoelastic recovery. All these steps are where my viscoelastic recovery, but we still have permanent deformation. And the more original strain there is, the more the permanent deformation exists. Another model that we did was we added annealing. Now, we had annealing in Marc before annealing was really treated as a load case. So, which is very common in heat transfer processes, right? We do some sort of thermal mechanical behavior. Then we basically put that material, let's say, in an oven or something like that to heat the material up again. The temperature goes above the recrystallization temperature, and we basically reduce the amount of permanent plasticity in the material. Here what we do is we basically say the annealing is really a material characteristic, and if we would have done both loading and temperature, we basically would have had our material undergoing increased loading, and there were some hold periods in here, but we would generate a certain amount of permanent strain, plastic strain. But then when the temperature got above this annealing temperature, which was 800 degrees here, temperature would increase, and that permanent strain would be removed. And you could say remove to zero permanent strain, or you could say I want a certain amount of permanent strain to continue to exist. Then when the temperature decreased, and when the temperature decreased underneath the anneal temperature, then effectively with continued structural load, we could resume and continue to have plasticity in the model. So it's an easy thing to apply. We just basically need to say what is the fraction of the current plastic strain that we want to recover, and what is the particular temperature at which we want this recovery process to occur. And so those would have been done directly on the plasticity menu, where we gave our yield stress and our work hardening curve. It would basically ask you if you wanted to define these particular behavior. And one of the things that you could do is you could basically say something like, I want the multiplication factor to be sort of a function of time as well. Another thing that we did in the area of material behavior was we introduced a couple of new anisotropic plasticity models. These are traditionally used in aluminum material, but it could be used in steel as well. You know, if we basically roll a metal, we basically induce anisotropy in the material, and then if we would form it, that anisotropy would influence the behavior. So the original model, of course, is the Hill model of anisotropic plasticity. Then many years ago, we introduced the so-called 5-model constant Barlat model. And in the meantime, we've introduced a couple of other models that have gained popularity. The 2014-18 material constant and the 2014-13 material constant. The big thing that these models do is they do a better job in capturing the 3D stress states of the material. And here's a typical example of what would happen. This was an axisymmetric punch. The initial sheath is axisymmetric as well. And effectively what happens, because of the initial anisotropy in the material, we basically create this what's called earring that occurs in the physical problem. And of course, again, everything can be introduced through the Mentat menus as well. The next thing I want to really talk about is element technology. Of course, we talk about the finite element method, and so elements are very important. So we've introduced a new family of elements into the Marc 2015 release. And they are very powerful elements. They're a new set of triangular and tetrahedral elements, and they've been introduced to overcome some of the shortcomings of the traditional elements. First of all, we know that traditional 3-noded triangles, 4-noded tetrahedral elements give very poor results for incompressible behavior. We also know that they are very stiff elements. So, of course, many years ago, or really over a decade ago, we introduced the family 155, 156, 157, which resolved many of the problems associated with incompressibility, but still basically were pretty stiff elements in terms of bending. So this new family of elements, they don't have any Lagrange multipliers. They only use displacement degrees of freedom, and that's good. That helps us out on 2 areas. It helps us out because we can use them with the iterative solver. The other thing is that we can use them in conjunction with all the material models that exist in Marc, whether or not it's a anisotropic plasticity model or a rubber model or whatever. And from your perspective, you really see them as traditional elements, but we actually internally add an additional node in the center. And we call these elements a strain smoothing element. So that's the term that you'll see in both the Marc documentation, volumes A, B, and C, and what you'll see in Mentat as well. And this is our very simple engineering example of what you can do. You know, if you took a beam model and you had a very crude mesh, and you use traditional lowest order element type 6, you would really see that you got really very poor results. And even if you went to mesh number D, your results were 11% off. And that was really effectively true with element 155 as well. But we see this new element, which is in the case of plane strain, element type 239, we see we really get very good results. And in the case of incompressible or nearly incompressible behavior, of course that traditional 3-node triangle, which we told you never to use, got even poorer results. The good news was element 155 captured the incompressible behavior, but still was not particularly good. And with this new element, again, we can see that we get much better results at every mesh than what we did before, and we capture the incompressible nature of rubber analysis, Ogden or Mooney, or any of them, or we capture incompressible plasticity. So this is always one of these traditional test problems. This, of course, is the standard linear triangle, which hopefully people haven't been using. But with this new element, we really get exactly the same result as we do with a fine mesh of quadrilateral elements, and we capture the necking of the model. Now, you don't get anything for nothing. The element can, because it has this great shear behavior, you can model very thin regions. You can basically use both the multiplicative plasticity, the FEFP formulation, or you can use the additive formulation. But the element is a little bit expensive. And really what we recommend is that you try to use the iterative solver, because the element generates a larger bandwidth than the conventional types of elements. Contact. We always, of course, are adding new capabilities to contact. What's really been introduced in this release, besides, of course, improving the reliability of the product, is we introduced a concept called cohesive contact. So many people, especially in the aerospace industry, but also true for automotive, is, you have a lot of individual fasteners. They could be rivets, or they could be spot welds. And one would love to do detailed analysis of every one of these connectors, but that would be too expensive. So we had a tendency to take problems, whether or not it's a lap joint or any sort of connector, and we said, we'll just do it with shell elements. We won't include the detailed analysis, and we'll use glued contact. And that's very simple to use. The problem was that glued contact was really effectively too stiff. So we basically didn't get as much displacements as what would be experimentally observed, or if we applied a displacement, we'd see too high a stresses. So we've introduced this concept called cohesive contact, and cohesive contact can only be used with the segment-to-segment procedure. And what it really does is, rather than say it's a glued contact or sort of infinite stiffness, we basically allow you to define what that stiffness factor is. And you could think about two problems, and this is really exaggerated deformation, but I'm allowing these two plates to have a little bit of sliding when I basically pull one relative to the other. And one can either introduce something like constant stiffness, or one could say that the stiffness is a function of the displacement, and these three different lines really represent what are the stresses at different levels along here. And one could then obtain what the particular stress is. So we can either define things as a cohesive stiffness, or what we can do is we can say what is the stress is a function of this opening deflection as well. And so how that's done is basically in the contact interaction menu. When you still basically say it's the glued type contact, but then you basically say, well, it's a special type of glue contact. I want to turn on these advanced glue settings. And then what it will allow you to do, and in this case, what the user did was they introduced a stress-based contact, both in the normal direction and the tangential direction. So they had slightly different curves. And the most important, they might look the same, but of course their values are different. And what they tried to do was represent the behavior of this type of connection. We have a beam or a plate that's clamped on this side, and then we have some spot welds here. So we basically used the C-weld capability. And really effectively, the blue line was based upon the C-welds, would have resulted our load deflection curve. And now using our cohesive contact, we basically would have gotten that particular behavior. And of course, if we would have done glued contact, we would have gotten even a higher type of resultant load in the simulation. One of the interesting things about introducing cohesive contact is we're really basically saying things are not infinitely stiff. So what you will see when you do a problem with cohesive contact, and especially if you don't have a very high resistance, is you will effectively see overlap in the model. So you will see bodies that look like they penetrate one another. Some people call this soft contact. Another area that I mentioned was we're always working to improve the fracture mechanics capabilities and the adaptive meshing capabilities. And really, they really kind of, in a certain sense, work together. The whole idea is to improve the mesh. And one of the things that we added was a concept that we call hard edges and soft edges, and projecting the new mesh on where we think that the new mesh should be based upon where your old mesh is. So even if you would have started with a mesh that looked like this, which was perhaps a pretty crude model, what you could basically do is you could say, well, I want a new mesh on this, and you might want to define a couple points to be hard points. Well, these it probably would have determined automatically, but you might have also wanted to say this point here was a hard point, and that point there was a hard point. And what the program will do is it will now put effectively a spline here, and it will generate a finite element mesh that's an improved mesh based upon this new projection technology. And the user can basically select these so-called hard edges and soft edges to kind of help the meshing procedure along. But there's really the goal of this was really to do things internally, having to improve the finite element process. And so what I really want to talk about is some other examples. This was a case where we had this body that basically had a change in the slope of this particular region. What we're really going to do is we're going to identify this as a soft edge. It shows up as in blue. Sometimes it's easier to do a wireframe. It might be easier to see. And when we're going to do something, what that soft edge is going to do is it's going to make sure that when we do remeshing in the simulation, that there are always element edges along that particular soft edge. So we're going to have this particular crack, and we're going to get to this here in a second. And then when the crack propagates over that transition in slope, there will be still edges aligned with that particular soft edge. And we see that in this particular example. So there are models where this is a very useful concept to utilize. The other one, of course, is you might have noticed this very nice mesh in this region as we propagated the crack. So what's going on is now whenever we're doing adaptive meshing, and we basically say we want to have a fine mesh near a particular location. In this case is basically a crack tip. We have our adaptive meshing. We say one of the criterions is a distance-based criteria. We say that we want it associated with the cracks. And we give it basically a couple pieces of information. We give it kind of the radius of influence and what should be the element size here. And then we give it basically a template radius and what the near crack radius is. And what that's going to result in is a nice finite element mesh near the crack tip propagation. And so what you're going to see now with fracture mechanics is a beautiful mesh that's aligned with the crack tip, and as the crack tip propagates, that finite element mesh propagates along with it. And the result, why do we do this? Well, basically, we observed that using a general adaptive meshers, we're not giving us good enough meshes to get accurate energy release calculations, which we then use for our stress intensity values and to determine the crack front direction. So now we get much more accurate results. We can get a better prediction of, let's say, the blunting of the cracks due to plasticity by having a finer and a better mesh in that vicinity. The last thing I think I want to talk about really, or no, I have one more after this, is a capability that we added for electrically controlled rigid bodies. And the application was really having to do with resistance welding. We had, of course, control nodes onto rigid bodies. They were really originally introduced for load-controlled rigid bodies. Now what we do is we basically say we can also have a load-controlled electrical rigid body. So before our rigid bodies were basically voltage controlled, and now what we can do when we say that we have this control node associated with the body, we can make it a current-controlled rigid body. So we could basically say I want to apply, 15 amps through the particular structure, and of course we would do a Joule heating analysis that would generate a particular temperature, and of course from that particular temperature we generate thermal strains and temperature-dependent material properties as well. As I mentioned, really the calendar year 2015 was very big year in terms of releases. We had released the Marc 2014.1 release, which was predominantly defect corrections. We also introduced the Marc 2014.2 release, which had really two capabilities. One was we introduced this CASI iterative solver with parallel processing capabilities. And effectively what one would see was that really if you run CASI in serial mode or if you run it in parallel mode, you could basically see somewhere between 2 to 2.5 times faster in the simulation. And of course, I'm bringing up CASI iterative solver again because really the usage of these new elements that I mentioned earlier, because they don't have Lagrange multipliers, because they generate a little bit bigger bandwidth than your conventional lower order elements, the iterative solver is often very appropriate for those types of problems. And of course, we can activate it directly through Mentat by saying that we want to use parallelization in the CASI solver, or we could introduce it directly through the command line using -NTS. The other thing, of course, that was introduced in Marc 2014.2 was the Adams-Marc co-simulation, which is a very general capability, a very powerful capability, but I don't really have the time to talk about it here. So, as we see, another capability feature of the iterative solver, the parallel iterative solver, is the improvements. First of all, even between 2014, so 2014 was a 1, 2014.2 often was faster than 2014, and then utilizing the parallelization, it would be even faster yet. But a lot of times, normally we think about parallelization helping bigger and bigger problems. Well, that's true here as well, but really what parallelization with the CASI solver does is it helps with ill-conditioned problems where we needed to have a lot of iteration. So the more iterations that you needed for the iterative solver, the bigger the improvement gain you will see with the new CASI parallel iterative solver. So before saying thanks, I should mention one last thing that's very important, and that is the Marc 2015 release is really available on the same platforms as the previous releases. So Windows 7, Red Hat 5.7 and 6.3, and SUSE 11.2. And we also know that the Marc 2015 release is also working just fine on the Windows 10 operating system, which is becoming more prevalent for desktop users. So I thank you very much for your attention. I think we have some time for some questions, which I am happy to answer.